Okay, so now I would like to discuss another example from the assignments. In the assignments, we had an exercise to define a labeling function for binary trees. And these were binary trees which had elements in the nodes. So we had a binary tree type called bin tree, parameterized over its element type A. And there were two possible constructors, that of a node, which was called bin, which has a left subtree, and an element of type A, and a right subtree. And then we had another constructor, empty, for leaves that contain no further information. And then we can create an example tree, let's say a tree of characters, by starting with a bin constructor, right, and then putting some character here. And then we need a left and a right subtree, and we can put another bin constructor here with another character, let's say an A, and perhaps also put another bin constructor here with yet another character. And then let's say here we actually have an empty, and here we put yet another bin constructor, but with empty and a Q and empty. And here we put an empty H empty. And here we put an empty R empty. Something like that. So this is a valid value of this bin tree type. If we print this out, okay, so I have a hole here for this labeling function. Let me replace this with undefined just for the time being so that I can load this into GHCI. If I print this out, it's all printed on one line, but it's still a tree like this. And then we would like to define a label tree function that takes a bin tree of A's and now attaches a unique number from left to right to all the nodes occurring in this tree. So the leftmost node should be labeled with 1, so the Q should get a 1 attached to it, the A should get a 2 attached to it, the X a 3, and so on and so forth. And if we try to do this using the standard design pattern, we will get stuck rather quickly. So if we do pattern matching and we distinguish between the empty and the bin case, right, then the empty case may still be easy, because if we get an empty tree in, we'll get an empty tree out. In fact, we are not aiming to change the shape of the tree at all. We want to have a tree out that has exactly the same shape, only the elements should be changed. So if the incoming tree is empty, that's fine. But in the bin tree, in the bin case, we are quickly getting into trouble, and we either need to need excessive helper functions in order to make progress, or we need to take a different approach. And why is this? Well, because already to determine what is the number that comes out of, that gets attached to this X, right, we need to somehow know how big is this left subtree. How many labels will we need in this left subtree? Right? So it's not enough to just, as we usually do, to just call label tree on the left subtree and get a new subtree out. That is not giving us enough information. That is giving us a new labeled subtree of the right type, perhaps, right? But now, in order to determine what is the right integer to attach to this X, we need to know how big was the left subtree, or how big is the relabeled left subtree. So we need to define another function that determines the size, which ultimately amounts to a new traversal or an additional traversal of the entire left subtree. That is a little bit unsatisfactory. And then even worse, when it comes to the right subtree, right, probably our label tree function would start labeling from 1 again. And would probably start labeling from scratch again, because we cannot say label from a particular number. So that means whatever comes out of the recursive call for the right subtree, we probably have to post-process and map over and increase all the labels again by a certain offset that only we know here, which again leads to the need of a different function, in this case a mapping function, which we may have, and an additional unnecessary traversal. So while this can be done in this style, right, we may think it is perhaps better, conceptually, if we could simulate the notion of having a counter, right? If we just have something like a counter variable that we can maintain while we are traversing this tree, and we can just look at what's the current value of the counter and use that and increment it whenever we use a number, right? Then perhaps the whole thing can be done in a more straightforward way. But now we are in a functional language, and something like a mutable variable does not really exist. But perhaps we can simulate it, right? So let's abandon this approach, and that was the idea in that assignment as well, given as a hint then, and instead take this approach with a simulated counter. And how do we simulate this counter? We simulate it in such a way that we simply say we get an incoming value for the counter, so an additional integer argument that tells us this is the next free label that you can use, or this is the label from which you should start labeling the current tree that you're considering, this tree. And then additionally, as an output, we not just give the relabeled tree, but we also give the final value of the counter at the end of the process, essentially the outcoming counter. After being done with labeling this tree, this is the next free label that someone else can use. So this is the input counter, the output counter. The idea is that this integer gives us the label we should start from, or the next free value that we can use, right, for counting the elements or attaching labels to the elements. And this is the final value that after we are done with our part of the tree, that is the next free value that someone else can use that comes after us. So that becomes the goal now. And then once we have this helper function, which has a different type, right, we can easily implement the original function by just saying, if we have a tree here, by just calling label tree args with the tree and with an initial counter value of 1, so that the idea is we want to start the entire tree, and the first label that we use should be 1. And then this is still type incorrect because it has the wrong result type. We get a pair of the relabeled tree and the final counter value out. But if we are really done with a complete tree, then we don't need the final counter value anymore, so we can simply extract the first component from this pair in order to get just the relabeled tree out. And that is the result we're actually interested in. So this is how we can recover the original type signature that we were aiming for in terms of the more general function that we are now trying to write. Right? And then we can go and try to write this one using pattern matching. And how do we do this? Well, again, we do consider the patterns, and let's call this one the incoming counter C0. And here we have bin left XR of C0. So in the case that the tree we want to relabel is empty, we still want to produce an empty tree back. And then the incoming counter value is the same as the outgoing counter value. because we haven't actually used any labels. Right? There weren't any elements in this tree, so we never had to increment the counter. So whatever counter value we got in is still free to use for someone who comes after us. Okay, so that case is still simple. Now here, the bin case is not quite as simple, but it is doable now. And the best way here is to operate with local declaration. So we're going to do some let in expression. Namely, the first thing we still want to do is we want to label the left subtree recursively. So we want to call label tree args on the left subtree, and whatever the incoming counter is that we are getting should be passed on to the left subtree, because we want to label from left to right. Right? So the next tree label, when we are called for the current subtree, should be passed on to the left subtree so that it gets used there. Unless that left subtree is empty, then we'll get the same thing out again. And now this recursive call gives us two results. It's giving us a new left subtree, the one with the labels attached, and it's giving us a new counter, namely the counter value that we get after being done with the left subtree. And this is the big achievement now, namely that at this point we can now say C1 is exactly the value that we want to attach to our x. Right? We want to reserve C1 for our x. And then if we label the right subtree, we do this using label tree args again, we are not feeding it C1, but we are feeding it C1 plus 1, because we have been using one value in the middle there for ourselves, for attaching to x. And then out of labeling the right subtree, again, we get two results, a new right subtree and a new counter value. And that's now the counter value that we have after we are done with the right subtree. And that is actually, then we are done with everything, because then we have been labeling the left subtree, we have been reserving the C1 value for the x, which we still have to actually use, and we have been labeling the right subtree from C1 plus 1, and we get C2 as the end result. So if we are done with all this, then C2 is the final counter value that we return for the whole bin node. And now we just have to construct the full relabeled subtree, and that is again a bin node, because we have been starting with a bin node and we're not changing the shape of the tree. And we use new L and we use new R. And for the element, we use a pair where we still have the old element in, and we use this reserved value C1. And this type checks, and because I've already defined label tree in terms of label tree args, I should be able to call label tree on our example tree and observe things happening. So if we compare this with the example tree, right, we had Q, A, X, H, B, R in that order, and now we have 1 attached to the Q, 2 attached to the A, 3 attached to the X, 4 attached to the H, 5 attached to the B, and 6 attached to the R. So this works. All right. And this is the solution that we've been aiming for back when we discussed this as an assignment. But I would argue that a little bit similar to the 3 lookups example that we had in the context of maybe, this is also a bit unsatisfactory. And why is it unsatisfactory? It's for slightly different reasons. It's not so much because it is so much noise, perhaps, right? I mean, the amount of noise is limited, and we can relatively clearly see by just looking at this definition that we are doing a recursive call labeling the left subtree and a recursive call labeling the right subtree, and we're then putting everything together. But it is because we have a really complicated flow of this counter, and that is the incoming counter is here, and then we pass it on to this computation, and we get a new value out here. And then actually we don't even directly pass it on here, but we reserve it here. And then we increment it by 1 here, right? And then we get a C2 out here, and that is then returned here. So we have these different versions of the variables, C0, C1, C2. And if you like, C1 plus 1 is really like a different version of the variable as well. We could even emphasize this and say we actually have like 3 versions of the counter by saying something like, let's say C2 at this point is C1 plus 1, right? And then we use C3 here and C2 here and C3 here. Right. Something like that, because I mean this is just like giving and then and now you already see, I mean, these kinds of operations, they're very dangerous. Let's actually verify that we haven't made a grave mistake now, but it still looks fine, right? Now C0, C1, C2, C3, they all have the same type. They're all of type int. If I make any mistake there with the threading, if I accidentally use the wrong in the wrong place, I get no type error whatsoever, but I get extremely wrong results, right? If I accidentally put C1 here, what happens? Suddenly all my tree is labeled with 1s because we somehow never increment anymore, right? Or if I accidentally put C2 here, this is actually wrong because now I have 2 definitions for C2. I mean, I could, for example, swap 2. Right? I could put C2 here and C3 here, and that would still work, at least type check. But now suddenly, well, it actually even starts labeling for a bit and it looks okay, but then we get into a loop because suddenly we have a cyclic dependency between things. Right, we are using something before it's actually available, but that is not type incorrect. It just leads to problems at runtime. So it's not so much the noise, it's the fragility of it all that I really object to. Right, but there is also a little bit of a noise component in that we have this counter argument that we needed to introduce as an extra thing, and we need to manually pass it everywhere. But primarily, it's this fragility that everything is very, very error prone. And in particular, if we later on restructure, like I just did, like do some form of refactoring and introduce a new intermediate step, then we have to somehow make sure that we like really thread all the different versions of our variable in the correct way. It's extremely easy to make mistakes with that. So it would be nice if we somehow can abstract from this notion of maintaining and passing on a counter, and if we can find a nicer way to do this. And now being at the stage where we are at, where we have already been discussing the maybe example, and this being the part on monads, it won't really come as a surprise that this is where we want to go again. We somehow want to like discover another type here that is an instance of monad. And in this particular case, it is a little bit harder to do so. It is it's not quite as obvious, it's not quite as straightforward as with the maybe case, where this nested case expression was out in the open and was extremely easy to just line up things. And I want to show this example as well, because sometimes you do have to like do a little bit of work to get things into the right pattern so that you can then detect that it actually is an instance of it. So this one is is harder to discover upfront. But now that we know where we want to go, we can actually move it into that direction so that we can then discover it. And in order to move it into that direction, we actually have to make it uglier at first. We have to introduce a couple of intermediate steps and refactor the definition a little bit to make the recurring pattern yet more pronounced. And then we can try to abstract from it and discover it again. And that's what we're going to do next.